Hello everyone and welcome to my presentation. So my name is Đức Lê and I am an undergraduate student at RIT. For the past year, I've been working on this project about conservation of extremal ellipticity and orbital angular momentum of astigmatic Gaussian beams. Together with Dr. Pan, my friend Nakif Kadir, my advisor Dr. Bhattacharya, and we also collaborated with Professor Kleinert, Dr. Kleinert, Professor Goen, and Professor Khare. So let's begin by talking about the Gaussian beam. So the Gaussian beams are usually created by lasers, and every Gaussian beam has a waist, also known as a focal point, where the radius is the smallest. As we move away from that waist, the beam radius actually increases according to this function. And across a cross-section of a Gaussian beam, the intensity will drop as you move away from the axis by a Gaussian function, hence the name Gaussian beam. So that is the intensity characterized by the real part of the exponent. And there's additionally, a Gaussian beam also has a phase characterized by the imaginary part. So for a Gaussian beam, there will be these spheres of constant phase, and each of them will have a distinct radius of curvature. Also is z-dependent. Additionally, there's also a Gui phase, which indicates that any Gaussian beam will incur a phase shift of pi as it moves away from, as it propagates through a focal point. And this figure is for an ideal Gaussian beam, which is rotationally symmetric. However, in reality, it is very, very difficult to achieve such ideal beams. In fact, most Gaussian beams are astigmatic. So this is about simple astigmatic Gaussian beams, which indicates there will be a non-simple astigmatic Gaussian beams, which we will discuss later on in this presentation. So for this beam, as you can see here in the mode function, the beam radii in the x and the y directions are no longer equal. The same with the radii of curvature in the x and the y direction. So the cross sections would be elliptical, and we would have ellipsoids of constant phase instead of spheres. And here are the cross sections in the x and the y direction. So the underlying cause for such discrepancies in gamma and r lies in two key factors. First is the asymmetry, which is the difference in the waist radii. As you can see here in the cross sections, the waist in x is a little narrower than the waist in y. Additionally, these waists are in different locations in the z-axis, as you can see here. So that is characterized by the second factor, the astigmatism. So these are the two key factors of a astigmatic Gaussian beam, and we would like to form our discussion around these two parameters. And because of the asymmetry, we would expect every cross-section to be elliptical. And additionally, because of astigmatism, this ellipticity also changes as the beam propagates. In fact, it will go through a maximal point and a minimum point, and we will call them extremal ellipticities. And this is a previous research has proven this relationship between extremal ellipticity and the asymmetry and astigmatism. So why should we care about this parameter? So interestingly, in the previous research, it has been proven that when an astigmatic Gaussian beam propagates through a symmetric lens, as we expect, a lot of parameters will change, like the asymmetry, the astigmatism. But there's one thing that will remain constant, which is the extremal ellipticity. So this is fascinating because it proposes a whole new class of propagation invariant. But in physics, there are only certain things that remain conserved, like energy, linear momentum, or angular momentum. So the main objective for our research would be to explain this conservation of extremal ellipticity using the conservation of orbital angular momentum. And we will do it for a diverse class of Gaussian beams, including the simple astigmatic beams in the fundamental and the higher order modes, as well as the general astigmatic beams. So let's begin with the simplest case, the fundamental simple astigmatic beam. So how are we going to find the orbital angular momentum? So the answer is to use quantum mechanical method. So that is to find the expectation value for the orbital angular momentum operator using this integral. So for the first moment of OAM, that is orbital angular momentum, is found to be 0 because people have already known that simple astigmatic Gaussian beams does not have a net OAM. However, the interesting thing comes when we find the second moment. It is actually non-zero, so that indicates that a simple astigmatic beam has a finite variance, and it is dependent on the difference in the radii of curvature and of the beam radii. So these two terms are z-dependent, but their sum, as you can see in the graph here, is actually a constant because OM has to be conserved as the beam propagates. Interestingly, we can also relate that second moment of OAM to the astigmatism and asymmetry. And as you recall, this expression for extremal ellipticity, these two parameters are very strikingly similar. So, in fact, we can relate the extremal ellipticity with the second moment of OAM by this very simple expression. So this is one of the most important results of our research. So why is it important? Because it indicates that the OAM, which is a very abstract parameter, can actually be found by finding the extremal ellipticity, which is very physical and easily measured. And since orbital angular momentum is well known to conserve upon propagation through any symmetric lens, we have proven the conservation of extremal ellipticity, so achieving the main objective of our research. The next step would be to move on these more complicated beams. So the first one we will tackle is the high order mid-Gaussian mode. So here is the fundamental mode that we have been discussing. And as we move on to the higher order modes, the cross sections become much more complicated. And here's the mode function. You can see the Hermite polynomials here. And for these beams, we were also able to find a relationship between the second moment of OM to the extremal ellipticity according to this expression, so, which looks a little bit more complicated, as you might expect. And so because of this relationship, we have expanded the proof of conservation of extremal ellipticity to these higher order beams. And the interesting thing you can see here is these m plus 1/2 and plus 1/2 terms are analogous to the higher energy of a quantum harmonic oscillator. And then we will move on to general astigmatic Gaussian beams. So mathematically, they are created by rotating a simple astigmatic beam by a imaginary angle I alpha. So what it does is it twists the beam, so the cross sections, the ellipse of the cross sections are no longer aligned with the x and the y axis, but instead they would rotate as the beam propagates. And in reality, this can be generated simply by propagating a simple astigmatic beam through a non-symmetric lens. And here's the mode function. That imaginary rotation is shown here as the hyperbolic sines and cosines. So unlike the simple astigmatic beam, this general astigmatic beam actually has a net orbital angular momentum. And we can relate it to the second moment of the corresponding simple astigmatic beam. And we can also relate the extremal ellipticity of the general astigmatic beam to the corresponding simple astigmatic beam, which is something new as far as we know. And as a result, we can also relate this mean OAM to the extremal ellipticity of general astigmatic beam. So, and again, because of this relation, we have expanded the proof to another class of Gaussian beam, the general astigmatic beam. And finally, we can use the ladder operator to generate the even higher order Hermite Gaussian modes for general astigmatic beams. And the result is the same. We can also relate OAM to the extremal ellipticity. So, in conclusion, the previous research has proposed a whole new class of propagation invariant, which is the extremal ellipticity, and our research has proven that the origin of such a new propagation invariant is simply the orbital angular momentum. And we have proven that for a very broad class of Gaussian beams, so general and simple astigmatic, for the fundamental and both the Hermite Gaussian modes. This new propagation invariant, the extremal ellipticity, is remarkable because it describes a trade-off between astigmatism and asymmetry. So in the past, people usually specify both the astigmatism and asymmetry when during manufacturing of ultra-precise lasers. However, since we have proven that they are related to, they are constrained by an invariant, it only makes sense to specify either of them because the other one would be constrained by the first one already. And as a result, because the requirements can be relaxed, we can actually reduce the cost of manufacturing ultra-precise micro-machining system, so which has applications in, for example, semiconductor lithography. And in the future, there are also works to do for this project. So one thing we can do is to prove that all moments of OAM can be related to the extremal ellipticity. So by far, we have proven that up to the 6th order OAM for simple astigmatic beams and 3rd order for general astigmatic beams. As we move on, the math becomes crazy, so that's surely something we should think about in the future. And array approach can also be another angle to look at this problem. That's the end of my presentation. I would like to thank Dr. Bhattacharya and Dr. Pan for giving me very helpful advices. My friend Akif for helping me throughout the research, and Professor and Dr. Kleinert for their collaborations. I would love to receive any comments or questions to my email address, which should be below in the description. And have a good one.